Today we will look at a topic which is relevant to harmonics and filters. We have seen that there are some harmonics that are always present, even if I consider the simplest model on the AC and DC sides. So, the simplest models of the converter, the simplest model of the AC side of the converter is just a 3-phase balanced voltage source, and the simplest model on the DC side is a constant current source. So, we know that there are harmonics in the AC side current and the DC side voltage. So, the sum of these harmonics, in fact infinite number of harmonics, to be precise half the number of harmonics are eliminated if I use what is known as a 12 pulse converter, but still there are harmonics. So, these harmonics are known as characteristic harmonics. Now, these harmonics are present in spite of having ideal conditions. So, say by ideal conditions what I mean is the AC voltages are actually balanced and the 3-phase network is symmetric. That means the impedance that comes on the AC side, the series resistance or series inductance are identical in all the 3 phases, and we also assume that the pulses are exactly given at the required instants. And with all these ideal conditions or assumptions, we get some harmonics. These are known as characteristic harmonics. Now, in practice, there can be unbalance in the voltages. There can be a difference in the resistance of the transformers of the which are feeding the two bridges in the 12 pulse LCC. If you take a 12 pulse LCC, there are two transformers, one YY connected transformer, one Y delta connected transformer. So, these two transformers have a resistance and a leakage inductance. So, there can be a difference in the resistance and leakage inductance of these two transformers. So, that will result in something which will not cancel out the harmonics. Say, if you take a 12 pulse LCC, some harmonics get eliminated. Now, that is based on some assumptions. So, one can actually prove, though we proved it in the case of ideal transformer, even if I add an impedance which includes the resistance and leakage reactance, as long as the leakage and reactance and the resistance are same for both the transformers, I can still eliminate. But if they are different, then there will not be complete cancellation. So, there are some harmonics which are supposed to be cancelled and do not get cancelled. So, they are called non-characteristic harmonics, and some harmonics are actually present due to other conditions which I just mentioned, unbalanced AC voltages, and the network itself, the 3-phase network itself is say not symmetric. We can actually categorize the harmonics into two types. One is characteristic harmonics, the other one is non-characteristic harmonics. So, first of all, let us define what is known as characteristic harmonics. So, characteristic harmonics are the harmonics that are always present, harmonics that are always present even under ideal conditions, even under ideal conditions or ideal operation. So, what we mean by ideal operation is balanced AC voltages in the 3 phases, and the 3-phase network itself is symmetric. So, symmetric 3-phase network. And the pulses are given at the right instants. That means, if I take a 6 pulse converter, if I give a gate pulse at some instant, exactly after 60 degrees, I have to give one more gate pulse to the next thyristor. Similarly, after 60 degrees, I have to give the next gate pulse. So, the distance between any two consecutive gate pulses should be same. So, we say equidistant pulses, equidistant pulses. So, this is the definition of characteristic harmonics. So, non-characteristic harmonics are harmonics other than characteristic harmonics. So, by definition, non-characteristic harmonics are harmonics of order other than those of characteristic harmonics. Now, as I said, there are many reasons for non-characteristic harmonics. So, these are due to I will list out some of the reasons. Imbalance in the operation of the two bridges. So, I am referring to the bridges of a 12 pulse converter, Then there can be firing angle errors. Now, the AC voltage itself can be unbalanced, or there can be distortion. See, we assume sinusoidal waveform. So, there can be distortion. Distortion means deviation from sinusoidal. So, unbalance and distortion in the AC voltages. Now, there can be an imbalance in the operation of the two bridges. There can be an imbalance in the two transformers also, as far as the resistance and leakage inductance is concerned. So, unequal resistance and or leakage reactance of transformers feeding the two bridges of the 12 pulse converter, of transformers feeding the two bridges of a 12 pulse converter. See, a bridge is a 6 pulse converter, feeding the two bridges of a 12 pulse converter. Yes.
One is you are saying that non-characteristic harmonics are those which are of other order than the characteristics.
Yes.
Is it possible that we have the same order and it's kind of
The same order also may have a change in the magnitude.
Yes.
That is also there.
That is also non-characteristic.
No, by definition, this is the definition. By definition, we call non-characteristics as those harmonics of order which are ideally not there, but they just come up because of these reasons.
Yes. And also it can be like if 11th order was having some magnitude A.
Now it will have a different, yes, yes, it may have.
That is also because of non-characteristic.
No. By definition, see, this is just a definition. The definition given in books is this. I mean, by non-characteristic, we mean an harmonic of order which was not there earlier, which has now come. Okay, but that does not mean that the characteristic harmonics will remain same. They may change in magnitude. They may change in magnitude due to these reasons. But it's unlikely that they will go away. It is still there. But we know that at least that order is there. Even in ideal operation, that order is there. So, what I am trying to say is, if you do some measurement using some meter, okay, so there are meters available to measure harmonics, you may see that some harmonics which are not supposed to there is coming. Suppose you take a meter and see fourth harmonic is there.
Yes.
Now you may be wondering why it is there. Ideally it should not be there, but it can come due to some reasons. So the reasons are these.
And one more question was that we are seeing unequal resistance and leakage. So since it is root 3 into the other one, it's almost like double number of turns. So length is double.
See, I made one assumption. You recall what? When I stated this assumption. I assumed that the resistance and leakage reactance are same. If they are not same, there will be no cancellation, perfect cancellation. I made that assumption. Now, that assumption is strictly not true, but the point is they are small. These resistances and leakage reactances are small. So, though there will be not complete elimination, there will be a drastic reduction in all those harmonics which are not supposed to be there ideally. Suppose I take fifth harmonic, it will not get completely eliminated. So, now a few things are actually stated in order to understand what is happening. So, under ideal conditions something happens, but in practice we never get that. In practice we never achieve that, obviously. But see, the point is this: a fifth harmonic is not zero, fifth harmonic component is 0. Okay, fifth harmonic component is 0.0001% of fundamental. Now in practice both are same. So that's what we get in practice. So there is a difference. Mathematically 0 and non-zero are different.
Yes.
But in practice what we mean by 0 is not 0, negligible. That's all. So these are the reasons which result in non-characteristic harmonics. So for example, okay, let me give an example. So this is just one example. There can be many other examples. Suppose I have fifth harmonic component in AC side current of 12 pulse converter. So I am giving an example of characteristic harmonic or non-characteristic harmonic. It is non-characteristic. See, fifth harmonic is characteristic for 6 pulse. For 6 pulse, for 12 pulse it is non-characteristic. It is not supposed to be there. Okay, so this is an example of non-characteristic harmonic. Okay, so that means what was supposed to be eliminated may not be eliminated if there is a large imbalance in the operation of the two bridges, or resistance and leakage reactances are not very close. Okay. So, instead of trying to give more examples, let us take one case in detail and see exactly the generation of a non-characteristic harmonics. So, there are many ways in which a non-characteristic harmonic can get generated. So, I said one of the reasons is firing angle error. So, let me take that example.